Guys, I'm representing team number 15-4 from College of Engineering, Pune. Here is the implementation of the first part of our problem statement. It is implemented using the ASLKV 2010 starter kit provided by TI. The problem statement states that we have to generate a square and a triangular wave by means of a Schmidt trigger and a Debu integrator. The Debu integrator works on the principle of the Howland current. Now let us see the output. As you can see here, the square wave has a peak-to-peak voltage of 14.8 volt and a duty cycle of approximately 50%. The frequency is 1.055 kilohertz. Let us switch to the triangular wave. The triangular wave has a peak-to-peak voltage of 10 volts and a duty cycle of approximately 50%. The frequency is approximately equal to that of the square wave. The problems which we faced while designing the first part was that the values, peak-to-peak values, were not matching with the values which were simulated, and hence we cross-verified the problem statement by implementing the same circuit on a breadboard. We got the same values, and the learning which we got was that we had no idea about a Debu integrator, which is a non-inverting integrator. After implementing this problem statement, we got an idea about the non-inverting integrator and how it works on the principle of Howland current.
Hi, this is the simulation of the part 1 of our problem statement. I will now show you the transient response. I'll place cursor so that you become clear about the peak-to-peak values. As you can see, we observe peaks at 5.82 and negative 5.83. Hence the peak-to-peak value will be 11.65. Now we'll look at the square wave. The peak is at 8.48 and negative 8.48. Hence we get a peak-to-peak value of 16.96. So guys, I'll now show you the output of the part A of our system on the oscilloscope. As you can see guys, we're getting a square wave which has a peak-to-peak voltage of 16.96 volts. Let me change to the second voltmeter. You can see guys that we've again got a triangular wave which has a peak-to-peak voltage of approximately 11.5 volts. For better clarity, let me maximize it. So that's all for the simulation guys. Thank you.
So guys, this is the implementation of the second part of our problem statement, which is the implementation of a voltage controlled oscillator by using the function generator created in the part 1 and a MPY634 analog multiplier IC in the positive feedback. As you can see, we've got a square and a triangular wave on screen. I will separate them for your convenience. The frequency is 250 Hz, and which is same for both of them, and the duty cycle is 50%. Now once more, as we vary the voltage, you can see on the screen that the frequency is changing. Varying the voltage even more will result in a greater frequency change. I'll keep on varying the voltage, and you can observe the frequency to be increasing. Observe that the frequency is slowly increasing as I vary the voltage. Hence, this is the implementation of a voltage controlled oscillator by using the analog multiplier IC provided by Texas Instruments. The learnings which we got in this was that we had never before we had implemented the voltage controlled oscillator by using something known as an analog multiplier, and hence this was the greatest learning which we got in this part of the experiment. This board provided by Texas Instruments is a very good board which is excellent for implementing basic circuits for learning, and hence that's all I have to say. Thank you.